Olá, como estão? Eu sou o professor Rodrigo Rezende. I'm professor of the postgraduate program in biotechnology from the University of Araraquara. And today I have the pleasure to bring to you the presentation, the lecture, The Health Revolution Promoted by 3D Technologies. This lecture will be presented by Dr. George Silva, who is the director of this Renato Information Technology Center in Campinas, São Paulo, Brazil. Dr. Silva is a PhD from the Faculty of Chemical Engineering at the State University of Campinas, Unicamp, Master in Electrical and Computer Engineering from Unicamp as well, and Electrical Engineering from the Federal University of Espírito Santo. He was a visiting researcher at the Institute of Industrial Automation in Spain, created and coordinated and still coordinates the nucleus of three-dimensional technologies, NT3D of CTI, Renato Research Center, that is under Ministry of Science, Technology and Innovations. Dr. Silva is one of the researchers responsible for the National Biofabrication Institute, ANCT Biofabrication, and board member of the International Society of Biofabrication. His areas of interest are additive manufacturing for multidisciplinary applications, 3D medical image processing, and CAD and BioCAD modeling and CAI simulations for medical applications. Dr. Silva is one of the most important references in additive manufacturing in Brazil and Latin America. So, would like to give you the welcome, George. It's a great pleasure to have you here as a very nice friend, personally, and as a reference in additive manufacturing and biofabrication, you are. Welcome.
Thank you, Rodrigo. Thank you for your words. And I'm very happy to be here with you. And I will welcome everybody to the Digital International Congress on Biofabrication, Bioprinted. It's an honor for us also to co-organize this Congress with Uniara. Uniara is organizing, and then we help them to do that. Rodrigo is a friend for a long time, and in fact, I'm very proud to be here. So my objective in this presentation is to give some whole information about CTI, what we did in the last years in the area of additive manufacturing for healthcare. So my idea is to give an overview about that. CTI is one of the research centers of the Brazilian Innovation Ministry, Science Technology Ministry. We are located in Campinas. Campinas is state of São Paulo, and we are one of the 20 institutes. When I assumed the directory of the institute in beginning of 19, end of 18, I put some focus on the Industry 4.0, advanced healthcare, that's our focus today, and some digital government, actions in digital government, and enabling technologies. I don't go further than this, but just to highlight that our institute is focused mainly in these 4 areas today. Especially in the group of 3D technologies, we are working this area since 97 or a little before. We started with the CAD system, and then additive manufacturing. I'll show later on this talk. And in this group, we work with additive manufacturing, also known as 3D printing. We work with the structured materials, mainly biomaterial for medical, developed since 2005, a platform, experimental platform for additive manufacturing, working on software and hardware, open software and open hardware. We work with medical imaging, anatomic modeling, and computer simulation and bioengineering. The last time, the more recently, we work with biofabrication. Biofabrication started at CTI in 2005, 2006, when I met people in Portugal, especially Dr. Miranov, that will give a talk in this, also in this conference. As I told you, since 97, when we installed the first machine, a SLS machine, selective laser sinter machine, at that time I had more hair, black hair, and less fat, so a long time ago. And we started that time when what the machine, the first part we printed was a skull. So we were very committed to work in the medical applications of bioprinting and bio additive manufacturing. After that, we tried many times to work with doctors, but they were very reactive to this approximation, to this approach. But after 1 or 2 years, we succeed to have them with us. So in 2000, we made a workshop in 3D printing for healthcare in Brazil, and we had many doctors. Those are one of the speakers of this workshop that time. 2011, we made the first workshop on bioprinting, 2D bioprinting. So it was more specific, the idea to use printing, 3D printing, to printing organs and tissues. So in that time, we had the Tulif Vilbert, that is a guy from Euphoria, Norway. He works with modeling, mathematical modeling of anything, but in that time we were interested to model organs. The guy black with suit black on the middle is Ivan Malone. Ivan Malone is from Cornell University. That time he finished his PhD and launched the first machine that was fab at home. That was one of the open platform for this application of additive manufacturing on the world. Myself and Vladimir Mironov on the right side. That time, but Vladimir was just coming to Brazil for a couple of weeks, and then after that, he stayed here for 2 years working with us. We have a good infrastructure at CTI, mainly related to additive manufacturing. We have powder machine, especially polymers. We have metal machines, and also filament machines. All of them are professional machines, wax machine and resin machine, but all of them are professional machine. But we also, as I said, we developed this infrastructure, these platforms for additive manufacturing that are experimental machine. I will show you later one of them. So what's the things about additive manufacturing? The most interesting thing is in additive manufacturing is that for the whole application, industry or medical application, but the background is that it's a digital technology. It means that if you can see a patent from Muntz in 51, this guy almost invented a 3D printing machine. You can see creation of a 3D model inside a vat or a chamber. That's the idea. That's the complete idea of a 3D printing. But that time, what happened? There is no computer available. So what happens after? Computer became less expensive. And then this idea, or many ideas about that, started to grow in additive manufacturing. Or in that time, long time ago, was rep prototyping in 90s, in the beginning, in the 80s. What's the basic for biofabrication or 3D technologies for biofabrication or for additive manufacturing, as you wish? You can see left side, you can see virtual. Virtual is the model Is the model you can come from any source, like scanners, like light scanners, like mathematical models in a CAD or BioCAD as you wish, or even computer simulation models. But one thing is interesting is that when you're talking about model, 3D model that you can export for a additive manufacturing machine is the medical scanner, because you can make you can take information about the anatomy of a patient, detailed information, and separate this information, then print it in the other side, on the other side of these dot lines, red dot lines, that are the technologies for 3D printing. And many applications arrive since you have a 3D model for a device, for example, for a medical device, or even for a biofabrication, if you have, for example, a model for a tissue or an organ in the left side. So the basic is you need a 3D model. This 3D model comes from a digital model that comes from a scanner, a medical scanner, like, for example, a foot. You can see, for example, this foot was segmented from a model in a CT scanner, a sequence of images of a CT scanner, and then with the specific software I'll show later on, you can virtually slice this model and send to machine. When you do that, you can create parts, or you can create physically models for any application. As I said, from a device, medical device, for an industry part, or even for biofabrication by tissue or organ, for example. So this is the basic for additive manufacturing in any phase. It means that beginning, and you have to have this model for additive manufacturing, for 2D printing, or even for bioprinting. You have to be based on models, on 3D models. So as I said, it's mainly a digital technology. I will go further on this, but we have lots of technologies in additive manufacturing. Here I'm showing only technologies that are related mainly with the industry, but can have also can be useful for medical applications. So you have lots of a myriad of process in this additive manufacturing area. The materials related with additive manufacturing are many today. Are many polymers, metals, and some alloys, ceramics, and the composite in between those materials. So you can have, for example, polymers and metals together. You can have polymers, ceramics. But one interesting thing is that you can have also biomaterials. Those materials can be biomaterials, polymers, metals, or ceramics, biomaterials, specific for the medical applications. And what's the most recent things today is the biomaterial that's living materials that are like cells, like agglomerate of cells, that you can use it as a biomaterial also. But what's the interesting thing with additive manufacturing? If you see, in one hand, you see mass production. Everything you do, you have to produce a lot of things to be cheap. On the other hand, you have artisan production. That means that it's very expensive to create something that is specific for somebody. And for us, additive manufacturing is a convergence in between mass production and artisan production to have the better of the both. So you have flexibility, you have production in a small machine or a confined machine, and you can change things all the time without a mass production, with that to set up a sequence of machines. So additive manufacturing is a mass production together, artisan production, a convergence. That's very interesting, like an industry in the healthcare, because everybody is different from each other. And also in areas like aerospace, when you have small production of very complex structure like planes, like satellites, and so on. This is one of technology we have at CTI, that's electron beam melting. This is a technology that beam melts down a powder bed, the metal powder bed. And then you can create parts, complex parts from this technology. It's mainly use TI alloys, titanium alloys. And you can create structure like this, called lattice structures, or structures that can have property as a bulk, properties different from the original material. So you can have meta materials, you can create different materials, or even functionally graded materials that you can start from one property and go to another property, change this structure in between those extremes. So what's the nice things for this is that you can have structures that you can, for example, to be in contact with bones, and bones can ingrow inside, because it's a very good structure for bones to ingrow inside. In terms of dimensions, additive manufacturing comes from big things like people are working machines that can build like buildings today, or even go to the right side, small things. One example is this ball. We call it a luck ball that we developed together with Dr. Mironov in 2013. That's an structure made of two-photon polymerization process. It's about 200 microns of diameter, and then you can encapsulate cells inside for some treatment or things like this. Another interesting thing for additive manufacturing is the legislation. Its standards are very important for communicate what you are thinking about, what you are producing, what are something needing in this context. So ISO is working with ASTM from the United States since 2014 to create a set of rules or a set of standards that can rule this area of additive manufacturing. But still, we need some standard for medical application. There are missing many standards for this area today. So it's a brand new area of standard that it's growing very fast, but we still need a standard for this area, especially medical applications. And then you have standards in feedstock materials, process equipment, and the finished parts. So in all of the stream, you have to have standards. When you are talking about healthcare market, it's a really big market on the world. If we are talking about, for example, Brazil is one of the countries that the life expectancy grew very fast, because we now have, since the 80s, we created a public system. In fact, we call it a universal system, because everybody that's in Brazil has the right to use our system. And then we grew our expectancy about 40 years in few decades. So today, the average Brazilian, in 2018, the average Brazilian expectancy is 76 years. If you see, in the 60s was about 52. So when I was born in 63, my expectancy of life was 55, about 55. So I should be officially dead this year, but I'm not interested to be dead. And on the left side, on top, you can see also the change of our population in Brazil, that in 2010, in the expectation 2050, how old people will be in Brazil. And then in bottom, you can see OECD information about how much a country that can invest in healthcare, health expenditure. You can see the biggest is USA with about 17% of GDP, and OECD is about 8.8% of GDP of average in the countries of OECD. And you can see Brazil 9.2. So it means that in Brazil, we invest more than the average of OECD in health expenditure. It means that it's a big market in Brazil. It means that our population will grow. The old population will grow so fast, is going so fast, and we need a lot of solution in this area. Well, at CTI, we have a cycle like to use every day. It's we receive image that come from a CT or MRI scanner. We work on software like Invesalis. Invesalis is a solution that we put available all over the world. We can simulate. We can design things or device. For example, we can simulate. We can print, and then we can send for surgery. This is a very common cycle in additive manufacturing for conventional use of this technology for medicine. See, now you can see a screen of Invesalis. It's a tumor in a mandible of a guy. You see the tumor is almost the same size of the skull. It's true. It's a reality in some countries, especially in Brazil. And you can see many. You can have many visualization of what you are interested in anatomy of a patient using Invesalis software. Invesalis is a software that we developed in our institute since 2000, and today is available for, you can download for this for free, completely for free, and it's open source. And now it's about 170 countries is using Invesalis. It's also translated in 16 languages. It's a cross-platform. You can use in Linux, in macOS, Windows, and so on. And to starting our concerns about reconstruction using information that comes from a specific patient. In this case, we have a guy that had a mandibular problem, and then we reconstruct this mandible with the bone that comes from the iliac crest. So computationally, we can take exact part of the bone that can fit on this part of the patient, see, like this. And then you can create also device that specifically can use during the surgery to cut part of the bone, like this one. And then this reconstruction. Also, you can do the same for a mandible, for a low jaw, when you use bone from a fibula, and then you take this specific bone from a fibula, and then we reconstruct. Sorry for this reddish picture. And also, you can use this kind of technology to generate molds, for example, for a cranioplasty using a very popular material called, for example, polymethyl methacrylate, that you can shape this on this mold and then fit for the patient during the surgery. This is a study we made with a surgeon in Hospital da Restauração in Northeast Brazil. 63 cranioplasty was made in patients that was big hole in the skull. And those patients, they call it the syndrome of atropinated. It means that those patients, they have lots of bad symptoms. And in this study, after the surgery and after 6 months of surgery, these symptoms almost disappeared in all of them. So it's a very, very cost-effective to treat this kind of lesion. The same is a surgical technique using this type of technology. And on the right side, you can see a prosthesis that a guy that had a second accident. Normally, people use, all around the world, they use to make this kind of prosthesis, but with metal. For example, titanium alloy, TI 64. But in this case, we're concerned very concerning about that, because if that case it were titanium, maybe this guy should have a bad problem. So the prosthesis was broken like as was planned using simulation processes like this. In this case, it's different because we need to adapt a prosthesis, and this prosthesis is adaptive for patients that are in growing age. So what means that we create like different parts that can slide on top of the other one and keep the brain safe for some impact or some perforation. This is the first time we did it, 2007. 2009, the guy was this child was almost in the childhood, but very well. 2014, the guy came to CTI, and it was interesting because we had at that time Brazil very, very hard drought. It means that almost 2 years without rain in that part of Brazil. And then I asked the guy how was feeling with this prosthesis. He said, "No, it's okay, it's perfect for me. But do you feel something too? Sometimes I feel like scratching when it will rain." I said, "What about today?" "Today is scratching." "Oh, okay. So it rained today?" "Yes, it rained. And during the night was a storm, really storm. So it's been useful also for weather forecast." In this case, this guy came again to CTI 15 days ago, 20 days ago, on the center. He's perfectly. So I have to say that we don't talk with the patient. This case was a specific case that the mother wanted to come and talk with us. And then this case, in this 15 days ago, he came with a reporter that made this reportage in time. The time he was a very, very young guy. Well, we also invest on dental applications, just to tell you that this is one of our paper, but we are not investing like selling, or we are not producing this solution as a, we don't sell this. In fact, what we do is research in this area. In this case, one of our paper was cover of a European Journal of Dentistry. And the next step is we are doing now is create this infrastructure that you don't use this kind of guide anymore. The guide is already the infrastructure, metal infrastructure that you can put together. I don't go further than this, but it increased a lot the accuracy of the process. Another thing is that we can also work with the facial prosthesis. This is a guy that lost a part of the eye and the bones. And then we developed together with the doctors monoscopic photogrammetry in the sequence of pictures that we can put together and then create a 3D model of the guy instead of using gypsum to mold this part. That's a very odd thing. The same with the old lady. She had a problem. She had a cancer in the nose, and what happens that she was took out the nose and the upper jaw, and then no way to talk, no way to drink, no way to eat, because there is no counterpart. And what's happened that we use all of this technology to put some screws and support this structure. That time, this nose was recreated from an old picture of the lady, and then she was very well, very happy with the prosthesis, and it was about 10 years ago, a little more. So just to summarize, we can use the additive manufacturing for many, many applications. Those are some that we use in CTI, at CTI for a long time. since aesthetic prostheses to molds and metal prostheses. And mainly in the center is, as I said, is Empresario software that we developed for this integration in between medical scanner and the additive manufacturing machines. We work also together with lots of hospitals in Brazil. We had more than 300 hospitals work together in Brazil, with some outside Brazil also. But when I'm thinking about the future, we have to think that our body don't want to have plastic or metal inside. Our body to want to heal by itself. So we were talking about processes that are not so complex things, but complex in terms of engineering, but not so complex things compared to biofabrication, bioprinting, and very, very low, a natural solution. It means that the process, metal process, is not natural for our body. But when you are growing the natural solution, you are also creating a major complexity of the solution. So you are growing in this scale for the scaffolds, for bioprinting, and even in vivo tissue printing. I will talk a little bit about that. I'm sure that our friends from Vladimir, from James Yu, from the United States, and Vladimir from Russia, and other guys will talk about this more specifically. So I don't spoil this their presentation. But mainly, biofabrication is a term that just arrived some years ago. That's inside tissue engineering, and that's inside medicine, regenerative medicine domain. That's a more long time in the area. And as a timeline, we can see that tissue engineering is not a new thing. We can see that about 938, a guy called Alexis Carrel, that was a French doctor, he was working with Lindbergh, the first guy that crossed the ocean, aviator crossing the ocean. They create some bioreactor to culture animal organs. So it was one of the first trials to keep organs alive without the body. So it grows. Christian Barnett made the first heart transplantation. So people in South Africa, so people that thought that time that they would never use something different than you have in your body. But donation is not so common. You have a lack of donors in all of the world. So it's still not a solution. You see the same, Dr. Skalak defined the term tissue engineering about 88, and Joseph Vagant and brothers create something that was very interesting, and published a very interesting article with a mouse with a ear on the back. And most recently, 2002, National Science Foundation established the consolidation, the tissue engineering, or as a multidisciplinary solution. So 2003 started the biofabrication in the timeline after this tissue engineering decision. So what's biofabrication? Also, my colleagues, I'm sure that I will show something that's more interesting, but one of the definitions today is that the biofabrication is the automated generation of biological functional products with structural organization from living cells, bioactive molecules, biomaterial cell aggregates such as microtissues, hybrid cell materials construct through bioprinting or bioassembly and subsequent tissue maturation processes. It means that it's a whole of things that you put together, mainly use automatic capacity to generate things, 3D things like additive manufacturing, and you put together and you create this kind of solution. It's a functional biological product. So there are many approaches that we can see for biofabrication. One, the first of them is to produce things like material that can be consumed in your body when you put inside your body, and it can dissolve like plastic or the material, and then you can create specific place for cells to grow inside, like an extracellular matrix. The same, but the material is different. Is on the right hand, it's organ printing that you are working with the more soft material like hydrogels, many different types of hydrogels, encapsulated cells, and then you create potentially you create organs also. This machine that we created in 2006 and was an open platform. It's still today it's running, and in this case we are printing the scaffold. So what's the nice with this machine like this? That's a very creative machine based on Fab at Home from Cornell Evan Malone. This is you can configure it. You can change material. In this case, we are printing with a micro screw head that you can put pellets on top and then create scaffolds from, in this case, polycaprolactone. At CTI, we use not only those platforms, experimental platform, but also commercial machines like selective laser sinter. You can change some parameters to run a big class of material. In this case, polymers or even some ceramics. And also, on the other hand, in the fused deposition modeling, like a screw I showed before, we can create scaffold to use lots of other materials, mixed materials and pure materials also. In this case, we printed dual scaled scaffold for tissue engineering, but also using electrospinning to create microfiber or nanofibers that cell can grow inside. And a little bit about bioink. What's a bioink? Bioink is a formulation of some kind of gel with cells inside. If you don't have cells inside to print, it's not bioink. It's just gel or just another material, a biomaterial. So the definition is that bioink is biomaterial with cells inside. And the origin of bioink can be from natural source like alginate, from algae, collagen, gelatin, bioinks, and the hyaluronic also. That's one material that we have inside our body, very common inside our body. Another source is synthetic source, like gelatin, polycaprolactone, as I said before, and material like glycols and pluronic, F127. Those are synthetic materials that you can encapsulate cells and print things using, for example, a bioextrusion process. This one is material we work together with those guys from UNICAP. In fact, is a PhD result from a friend of ours. He's working with us at CTI today. José Luis worked with Dr. Akira, and they developed some materials based on the alginate, and this alginate was put together with the nanosilicate, that's a laponite, the nanosilicate, to change the rheology of the material. What means that we have a shear thinning material. When you put in a syringe, you press, you put some big force here, then you have some shear stress in the tip. When you have shear stress, this material can melt down and be in a kind of liquid. After that, after leaving the tip, this material starts again to recover this viscosity. When it recovers its viscosity, it comes again a hard material. So it's a very interesting solution, for example, to create scaffolds with hydrogels that can change from one viscosity to another viscosity, and again back to the original viscosity. So spheroids are the block buildings of biofabrication. That's not cells itself, but a agglomerate of cells, normally in a rounded shape. And you can create spheroids from many different sources. And I don't go further on this, but at CTI we work together with some friends, some colleagues, to create micromodel non-adhesive hydrogels. And you can see here those like stamps that you can create micro molds. It was printed in a additive manufacturing machine like this, and then you can use to stamp in a biomaterial like alginate, and then by suspension, you have a suspension of cells. Those cells goes down to the bottom of the well, and this well can create spheroids. Spheroids with a very uniform diameters. Also, as I said before, this is a way to encapsulate cells, more or less the size of an spheroid, 100 to 200 micrometers, and it was published 2013. It was a work with, we printed using two-photo polymerization process. We printed this kind of burr, and this material can attach each other using some hooks and loops. So, in short, when you're talking about bioprinters, we have to think about the control systems, a feedback system that can, for example, for imaging or for sensors with temperature and something, you have to have control feedback for this. You have to control a chamber with an environment, a controlled environment, and a robot dispensing systems. There are many different technologies, but it's just a concept. And then you have to have online monitoring, like the quality you are producing. So it's probably will be one of the standards requirements for bioprint is that you have to have a traceability. You have to see what you are producing for medical applications. I go fast on this, but bioprinting, specific to print materials, soft materials, you can have in many shapes, like micro extrusion systems. There are some with pistons or using some kind of valve-based nozzle, but that's basically you have something that you press on top, and then you can deliver material on the bottom of the structure. The same you can use inkjet technology, like this cartridge for printing, regular printing. Instead of have a ink inside, or you have some bio ink cells with gels that you can print using this small nozzle also, and form of droplets. So you can create shapes using this technology also. One interesting thing, technology for me, is a laser-based cell printing, that you have like a carbon copy, you have cells, you have structured with hydrogels in cells here, and then you put a pulse of laser, a very quick pulse, with the high energy, very big energy, and you take out this material and you deposit in a platform, like a collector slide. What's the advantage of this technology? Very fast. You can create structure very, very fast, but you have low density of cells. That's a drawback of this technology. Another technology to create some structures in 3D is mainly from Japan. Is shish kebab, we call it shish kebab. It's skewering of tissue spheroid. In fact, are small needles, very, very thin needles that you can skew some spheroids, and then they grow together, they connect each other and create tubes. So it's a specific solution to create tubes like artery and veins, but if you solve these, it's a great step for regenerative medicine. When you're talking about bioprintings, you can see many producers in the world. You can see very expensive technologies, or you can see less expensive technology. Each of them has an application, but or flexibility to use different material. But you can work with, if you want, with also very cheap technologies. Here in Brazil, we have also companies that are specialized in this area, like those 3 companies. I'm very proud to know everybody in Brazil in this area. So I'm very honored to to see those companies growing, and I hope they grow very fast. Well, another technology that supports bioprinting is the simulation process. Simulation is very important. For example, if you're talking about a plane, without simulation, you cannot have a plane approved for FAA, Federal Aviation in the United States, because you have to do many things before you produce something. So in this area, it will not be different. For example, you can simulate cells, how it can grow, or agglomerate of cells. You can go in cartilage, like spheroids. This is mechanical simulation. This is a biological simulation, CFD simulation, computer fluid simulation of artery, mechanical simulation of a device inside the back, for example, or even some adaptation of instruments or some device in your body when you need for some needs. And what happens is that it's a very complex scale that integrate each of them together is a very complex process. But you are talking about models. So one thing that you have to remember is that every model is essentially wrong, but some has to be useful. This is a quote of George Box, a mathematician, that's for me very interesting. Well, we can talk a little bit. That's I'm sure that James, you show, and Vladimir will show many different solutions, but I will talk a little bit about these solutions that they are commercially available today, like a small organoids. This is a company called Organo from USA, one of the pioneers in this area. They are producing some small structures, some small tissues that you can use for drug screening, and many companies are using. Some companies are using now for developing new drugs. So, what's the scenario of biofabrication today? Today, we are talking about small things, small spheroids, organoids that you can develop some drug testing, or you can use as to substitute animals for any applications. Tomorrow, we would see small tissues, and then in the future, we will see completely organs for transplantation to replace organs and tissues that suffered for damage and things like this. So we are going to a personalized medicine, like a medicine we can call, if you want, 4.0. But one thing that we have to have in mind is that biofabrication is mainly is a technology that is still growing, is still in its infancy, but it needs integration of lots of area of different disciplines. Like since you are talking about imaging, artificial intelligence, data mining, modeling, simulation, computer simulation, interoperability among systems, optimization, design, and then you need all of them, biologists, doctors, clinicals, otherwise this technology cannot grow. So it's completely interdisciplinary area. Those are companies that can produce or are selling products in the TRL of those companies, but none of them are producing big tissues or something that for transplantation. They are producing small things, in more majority for drug screening. So those are companies in Brazil that also are working in this area. Just to tell that as industry grow a lot for industry 4.0 or advanced manufacturing, the medicine has to be also to grow also for this more technological area, more digital applications. So digital is the base for also biofabrication. Everything is based on digital technologies. Just to tell you that this paper published in 2019 in the International Journal of Bioprinting, I have to tell that I don't know those guys, but they put Brazil as a reference in Latin America, and CTI is the most publisher in the Latin America and the reference pioneer in this area of biofabrication. So it's a proud for us to see that our effort from almost 10 years ago, more than this, is now giving some results for the academy. In short, I should say that we are seeing in the medical applications, use additive manufacturing, bioprinting, we are seeing just the beginning, just the infancy of this technology. Remember that the transistor factor was discovered in 48. And then this was the first transistor. The first transistor was something like big one and strange things, odd thing, and then became something that you have in your hands today, a cellular with millions of transistors. So we are seeing today is about like this. In biofabrication, we are seeing the basic, just the infancy of the technology. We don't know exactly what we will grow to, but I'm sure that we will see organs and tissues in the near future. So my final consideration will be that this is paramount for modern medicine, 3D technologies in the whole. The medical device is strongly applying 3D technologies. It's growing very fast, especially for device that you can use for daily use. Cost effectiveness is very good for healthcare systems. It means that you can down the price, the costs of surgery, for example. You can solve the problem of shortage of organs. For example, the future use biofabrication concept and the production, I hope. It's a strategic area because biofabrication is today few countries are developing this area. So who develops first will be the winner. Probably we don't have one winner, but some winners on the world. So it's important that countries like Brazil and other developing countries were involved in this area to produce solutions. And a complete cycle of design, modeling, integration, quality control, optimization are key elements for the biofabrication field. Mainly when you are thinking about regulations, you are thinking about standards, because you have to pass all of these to have standards. The other thing is necessary to introduce as I told you, the interdisciplinary approach in biofabrication. Each more to have different ideas, different concepts inside this area. And as I said, also biofabrication is still in its infancy, but huge potential for market. And the one concern is not only the biological concern, but you have to have all the other concerns like cyber safety concerns. We are thinking about that those technologies in the future will be completely integrated with, for example, internet network. So if you are producing some organs from somebody, for example, this machine will be connected to the internet. Imagine, for example, somebody can enter and change something in the machine, and then you can produce a bad organ. So you can kill people. You can create some bad things for people that receive those organs or tissues. So in my concern, cyber safety is always a big concern in this area also. So I want to thank our financial support. It's FAPESP, CNPq, Ministério da Saúde, Brazilian Health Ministry, European FP7, some INCT like Biofabris, Regenera, CAPS, Petrobras, and FINEP. Thank you very much for your attention. I hope this presentation can give you some extra information that you don't know, and I'm available. That's my email, and I'm available for contacts.
Dear George, thank you. Congratulations for your nice presentation. To me, who knows you 1 decade and a half probably, and work together directly from during one decade. And we surely will continue this friendship and works together. And it's nice to see all your presentation and to see that I feel myself very proud, yes, about these developments. And thank you for taking your busy time. I know very well how difficult it is to have some 1-2 hours to give us.
No, it's my pleasure, Rodrigo, and my pleasure to work with all of you, and see that you still have a very good network of partners. In a conference like this, you can gather lots of very interesting people from outside Brazil. So it's really important. And also, I could not imagine 6 months ago, 8 months ago, a conference like this that we can work like almost for free. We have these nice guys, nice presentations together, very interesting information. So I thank you very much. I thank Uniara for the opportunity to cooperate with, and we are always available.
Thank you, George. See you next time.
See you.